cover electron beam and plasma arc machining. So EBM dengan PAM, these two topics. So the first topic we want to cover is electron beam machining. So this is this particular machining process actually uses electron beam for the material removal processes. So if you remember when we cover the EBM process, electrons also involved, because what you do is basically you do the bias between the electrode and workpiece material. And because of the bias, once the voltage gets certain level, and the gap between the electrode and the workpiece get to certain level, then basically what you have is we have electrons that can jump from the electrode to the workpiece. Then ionization happens, so on and so forth. Right? So it's kind of like similar principle can be used in this EBM machining process. So let's go through the first slide. So this is a page number 2. EBM is one of the several industrial process that use electron beams. As mentioned before, after this, when we talk about a laser beam machining, we will also use electrons beam as a machining process. The principle of removal is a bit different. Besides machining, other applications of the technology include heat treating, and also welding. So EBM can also be used for heat treatment and also welding. So heat treatments means that if you want to apply certain heat to a localized area of the workpiece for heat treatment purpose, or welding, then you can use this particular process also. And for this process, let me just mute the rest. So if you have any questions, just raise up your hand and we'll go back to you, or you can unmute yourself and you can ask questions. Right? Basically, for this EBM process, it uses a high energy focused electron beam. It's made to impinge on the workpiece at a spot size of 10 to 100 microns. So basically, the spot size of the material removal is very small. So you're talking about 10 to 100 microns. So the focus area is very, very small. And the mechanism is basically the kinetic energy of high velocity of electrons is converted to heat energy as electrons strike the work material. So basically, the reason why you can remove the materials with this particular methods is when you accelerate the electrons. Electrons will have very high velocity, even though the mass is very small, but the velocity is very high. And basically, once it's collided with the workpiece materials, then you have energy transformations from kinetic to heat energy. So this heat energy is the one that actually going to remove the materials, melt the materials and remove it. It uses high velocity stream of electrons focused on the workpiece surface to remove materials by melting and vaporization. So this is a method, melting and vaporization. So the same thing that we mentioned when we talked about EDM process last time. Okay? The way the electron is generated, basically you have electron beam gun, and this EBM process, it required vacuum. Otherwise, electrons would interact with air molecules. Thus, they have lose their energy and cutting ability. So you want to have a directional movement of the electrons to hit and impinge on the workpiece. So if you want to do that, basically you don't want the electron to collide with so many other atoms. So in order for you to prevent the collisions between electrons and other atoms, there'll be some collisions, but not that many. Then basically you have to establish vacuum conditions in the working process, in the working chamber. So it involves vacuum. So whenever you have vacuum involved in any process, then maintenance is going to be high, because it's very high maintenance to maintain a vacuum system. Any questions on the first page? So this is a schematic of the EBM process. So if you look at this particular schematic, so basically this is the vacuum chamber. So all this is the vacuum chamber. So the workpiece need to be placed inside the chamber, and inside that chamber is vacuum. Right? So basically, if you look at this is you have cathode over here, and you have anode over here. There are two ways of doing this. Anode can be here, or anode can be on the workpiece. We're going to talk about that later. But in this schematic, we have a cathode here, you have anode, and basically then basically because of that cathode and anodes, basically if the voltage is high enough, then basically you can have electrons. You can pull electrons from the cathodes to the anodes, and will accelerate, move through the chamber over here, and go through magnetic lens and deflection coils before it hits on the workpiece. We're going to discuss a bit detail on what happened in between the cathodes and workpiece later on. Any questions? Okay, the principle of it is basically so the electron beam gun generate the electrons from high voltage supply attached to the cathodes. So if you hit certain element high enough in terms of voltage, so on and so forth, then basically you can dislodge electrons from its atom and accelerate them to sufficiently high velocity and direct the beam to the workpiece through a small spot. So basically this is the cathode. So you apply a high voltage to it. So you're talking about 30 kV. This is a DC, not AC. So if high voltage is established between the cathodes and also the anodes, then basically you're going to have electrons going, you can pull electrons, accelerate electrons from the cathodes to the anodes. The cathode is generally made of tungsten or tantalum filament. So usually the cathodes is either tungsten or tantalum filament, because it has a high melting temperature. So you can have a temperature up to 2500 to 3000 Celsius. So this is needed because at this particular temperature, then you can dislodge electrons. Ions are generated from high power supply at the range of 150 to 200 kilovolt to create velocity over 200,000 kilometer per second. So you're talking about the velocity. This is the velocity of the electron itself, based on this particular voltage potential difference. Just after the cathodes, there's a grid cup which functions to focus the illustrated electrons. So they travel through the hole in the anodes. The grid cup is set at the high bias, negative bias conditions to prevent electron from divergence. So there's a grid here. So from here, electrons accelerate to the anodes, and there's a grid here. And the grid is negatively biased. So the purpose why the grid is negatively biased, so that you can control the movement of the electrons itself, right? Because I mean, if you have a grid on the side, then the electrons will focus on certain area only, because you don't want to go to the grid side because it's negatively charged. They are not now attracted to the electron beam and gradually get accelerated. As they leave the anode section, the electron may achieve velocity as high of half of the velocity of light. So the electron will travel at that particular speed, half of the velocity of light. After the anodes, the electron beam passed through a series of magnetic lens and aperture. The magnetic lens shape the beam and try to reduce the divergence. So basically what you have here, um, so even though the grid try to focus it at certain level, but you still have divergence of electrons. So there's this magnetic lens will try to will focus the beams back again, and also there's a deflection coils that actually deflect the stray electrons, so that you can have a stream of electrons, nice stream of electrons going through and impinge on the workpiece. So that's what it meant by here, where you have electron pass a series of magnetic lens and aperture, and magnetic lens shape the beam and try to reduce the divergence. Aperture, on the other hand, allows only convergent electron to pass and capture the divergent low electron from the fringe. This way, the aperture and magnetic lens improve the quality of electron beam. So basically, this basically the magnetic lens focus the beam, and there is aperture here, which is not shown here. The aperture actually deflect those electrons that diverge from the mainstream. So you can have a nice stream of electrons going through the aperture. Any questions so far? Then the electron beam pass through the final section of electromagnetic lens and deflected coils. The electromagnetic lens focus the electron beams to the desired spots, and deflection coils can maneuver the electron beams to a small amount of motion. So basically what you want to have is you apply a high voltage here. So this is negatively charged, and there's a positively charged anode. So because of that, then electrons get attracted down here. So you accelerate the electrons towards the anode, and basically after the anode, then you have a grid, and that grid basically dictate and focus the electrons going through it. And this grid is actually rotating, and we're going to talk a bit on it later on, because what it does is actually it induces the negative and negative bias on and off, so that you can have a pulse over here. So the electrons accelerated down towards the magnetic lens, towards the workpiece, and at this particular junctions, the electron speed is half the speed of the sound. So the magnetic lens will actually focus the beam, and you have aperture somewhere here to limit and deflect the stray electrons. So you have a nice beam of electrons going and impinge on the workpiece. So once electron impinge on the workpiece, then you convert the kinetic energy of the electrons to the heat, and basically the vaporizations of the workpiece material happen on the workpiece. Any questions? Okay, we're going to go to slide number 5, a principle of EBM, a mechanism of material removal. So you can see there are 4 schematic in here. So the electron gun produce high energy focused beam, which is made to invade the workpiece with a spot size of 10 to 200 microns. So basically the size, the localized heating is done on the spot size, and this spot size is 10 to 200 microns. As a beam strike the surface of the workpiece, the kinetic energy of the high velocity electrons converted to heat energy. So I explained that just now. So because of that, then the spot getting bigger and deeper due to the melting and vaporizations of the material caused by the high power density. So as time goes by, then basically the material will be melted and vaporized. So it become deeper. This process will be carried out until the desired depth is created. The molten materials, as the product of the materials removed process, will be casted out from the cutting zone by high vapor pressure of the lower part. So basically, so if you look at these materials, so this is a workpiece. What you see here is workpiece, and this is the they call it auxiliary materials, auxiliary support ataupun auxiliary materials. So basically, once the what you call it, once the electron hit the surface, so kinetic energy is converted into heat, right? So you have a melting of vaporization, melting of materials here. So as time goes by, then basically you have formations of a hole, right? And once it penetrates through the auxiliary support, what happened then? These auxiliary support materials will be melted and vaporized also, and this actually produce a pressure that actually push out the molten materials from this hole out. So this auxiliary support system support material, the purpose, the second purpose other than supporting the materials, the workpiece materials, is also acted to be converted into vapor and induce a vapor pressure that push the molten metals, vaporized materials out from the hole once it's got the in that particular sections. Okay. Process parameter for the EBM. So there are few there are three most important parameters related to EBM. The first one is beam current. So this is adjustable from 10 gigaamps to 1 amps. As the setting of the beam current is increased, the amount of energy per pulse delivered to the workpiece also increase. So currents actually uh, uh, control and dictate the amount of energy per pulse. Because if you remember, energy is basically is a product of voltage and also current. Electron beam machine can facilitate up to 120 joules per pulse, which explain the ability of a process to rapidly drill very deep and make a large diameter hole. So secondly is pulse duration. Pulse duration affect both the depth and the diameter of the hole. The longer the pulse duration, the wider the diameter and deeper the drilling depth capability will be. Typically, electrons beam system can generate pulse as short as 50. So this is not TI second. This is microsecond. This is microsecond. So change that from TI second to microseconds, or as long as uh, 10 uh, milliseconds. So between 50 microseconds to 10 milliseconds. So if you look at this, the pulse durations. So the pulse duration, the effect of pulse duration is both the depth and diameter of the hole. So the longer the pulse duration, the wider the diameter of the hole and the deeper the drilling is. So you have to be careful when you adjust the pulse duration. So if you look at the T on for the pulse durations to be long, then you're going to have a wider diameter of a hole. Okay? Next is lens current. Lens current is used as a parameter to determine the working distance as well as the spot size of the beam. To achieve the desired hole diameter, the beam power must be able to generate more than 108 watts per cm squared, or else the power density will be insufficient to do heating and vaporizations. So you also have a lens current. The lens current is determine the working distance as well as spot size. So this is basically the lens current, which will dictate the spot size of this and the focal point. So you can actually adjust where the electrons will focus on the workpiece. Is it on the surface or a bit below the surface of the workpiece? So these are the three main parameters that important in EBM process. There are other process parameters. Other process parameters that are still affecting the machining characteristic of electron beam, which are the accelerating voltage applied. So we have accelerating voltage applied, energy per pulse, spot size, power density, and melting temperature of the workpiece. Any questions so far? This is talking about the process capabilities of the EBM. So what can EBM do? Right? So EBM can provide hole diameter range between 100 microns to 2 millimeters. with a depth up to 15 millimeters. So the capability that not many process has. So you can actually uh, drill a hole about 100 microns to a depth of 15 millimeters. So if you want to do this with drilling bits, you cannot do it. And the length to diameter ratio is around 10. So you can do length to diameter ratio around 10. The hole can be tapered along the depth or barrel shape. So you can taper along the depth or barrel shape. So you can either have the whole, you can either taper it to have a taper, or you can have it a barrel shape. So basically this is the capability of EBM. But focusing the beam below the surface, a reverse taper can also be obtained. So if you want to have a reverse taper, means that you want to have higher, what it means by reverse taper is this. So reverse taper is basically if you want a hole, so if you want to have a whole taper like so, let me try this. That's a reverse taper, right? So usually a taper hole looks like this, right? Bigger at the top, small at the bottom. So you can have a reverse. You can have a reverse taper. So this is a reverse taper. So if you want to have this reverse taper, then basically you focus the beam below the surface. So rather than focusing the beam on the surface, you focus the focal point of the beam is somewhere here. Right? So you can have this reverse taper. Generally, burr formation does not occur with EBM. A wide range of materials such as steel, stainless steel, titanium, so on and so forth, as well as plastic, ceramic, can be machined successfully using electron beam. So basically, again, the principle of material removal for EBM is actually vaporization. So because of that, then basically the strength of the material is not important. What important is the melting point. And since you can create a lot of heat, generate a lot of heat using this particular process, you can melt almost anything using this particular process. So because of that, then you can machine almost all materials. Any questions? Okay. Here it is. Okay. Let's look at the surface finish, heat affected zone, and tolerance of EBM. So these are something that you have to consider when you want to select this particular process to machine something. So you have to look at the effect of the surface finish, heat affected zone, and also tolerance of EBM. So a cutting edge quality is dependent on the type of material. So the cutting edge quality actually depends on type of material, depending on the type of material that you use. Local pitting commonly happen. The amount is influenced by the thermal properties of the workpiece, the pulse energy or pulse charge. The surface finish is boosting if the pulse charge is increased. So you have to remember this. As mentioned just now, you can actually pulse is one of the important parameter in EBM, and it does not only affect the size of the hole that you machine, but you can also have pitting issues, and also you can have uh, what do you call it? Thermal uh, surface finish issue if the pulse charge is increased. So again, as I mentioned just now, the pulse is at the grid is set at the grid of the apparatus. The machine layer, surface layer, is affected by high temperature. The thickness of the affected layers with the increase of the pulse breadth and hole diameter, common value of tolerance is 0.05 millimeter. So basically, talking about the tolerance is plus minus 0.05 millimeter. So you can consider EBM as a precision cutting techniques. In drilling, so if you want to do drilling, tolerance of plus minus 5% of the beam diameter is possible. So basically, if you set the beam diameter at certain, let's say for example, 100 microns, then you should expect plus minus 5% of tolerance of the hole that we generated. For drilling the same hole size, the hole tolerance will increase if the thickness of the workpiece is increased. So this hole tolerance will increase if the thickness of the workpiece is increased. For example, 0.5 millimeter if the workpiece thickness 0.3 millimeter, hole tolerance is 4%. Right? And 0.5 millimeter is 5%, and 1 millimeter is 7%. So it depends on the hole size. Then basically the tolerance also will increase. For any workpiece materials, tolerance also increase if the whole drill size is increased. So the EBM process is a precision machining process with a very good tolerance, 5%. But it depends on the hole size and the depth of the hole that you want to drill. Any questions?
No, sir.
Okay, process capability of EBM. So EBM is used for a variety of high precision cutting applications, including drilling, extremely small diameter hole. You're talking about down to 0.05 millimeter. Drilling of hole with a very high depth to diameter ratio. Just now we're talking about 1 to 10. And cutting slot, they are about 0.0025 millimeter wide. So if you want to cut the slot of this width, 0.025 millimeter, then you can do it using EBM. There's no toolware involved in it. The process is ideal for micromachining and generally limited to cutting operation in thin parts in the range of 0.25 to 6.3. So usually ideal for micromachining and for thin, limited to thin parts. So if you want to do micromachining, limited to thin parts in the range of 0.25 to 6.3 millimeter thickness. If you go deeper, then basically the tolerance will become worse, as mentioned just now. So you're talking about the tolerance of up to 9% if you're looking at diameter of 4 mm, so on and so forth. So these are some of the applications of EBM. Drilling a hole, pressure differential device using a nuclear reactor, aircraft engine, so on and so forth. So if you want to have a drill a hole in pressure differential device, a pressure differential device is a hole that balance the pressure outside and inside. For example, if you take a flight, if you sit in the window seat, right? So if you look at the what do you call it? At the window of the glass or plexiglass of the plane, you can see a drilling hole between the inside, between the layer of the glass of plexiglass. So the purpose of that particular holes is basically for this pressure differential device. Machining a wire drawing dies having a small cross section. So if you want to draw a wire, so you need to have to manufacture the die, fabricate the die with the size of the wire that you want. So if you're talking about gold wire for wire bonding in semiconductor applications, you're talking about maybe 10 microns of wire. So you need to be able to drill a hole of that size in order to make that wire. Or preparation of thin sheets, so you can make a slot on the thin sheet. Integrated circuit fabrication, 3D printing of metals. So it's one of the application of EBM is 3D printing of metals. Means that you can do, so this is not for machining. This is for heat treatment, meaning that you can actually fuse the powdered metals at certain location that you want. So then you can add for the 3D printing of metals. So you can use EBM for the process. And you can also use EBM for annealing of the welding process and welding process. So you can do spot annealing and you can do welding process using this particular EBM techniques. Advantages of EBM. Basically, drilling is possible at high rates up to 4,000 volts per second. So this is a very fast operation. No difficulties counted with acute angles. So you can make acute angle means that you can drill holes at an angle without much an issue. So acute angle basically, if let's say for example, if I have this block like that, and usually you drill from here, but if let's say for example, if you want to drill at an angle like this, right? So it shouldn't be an issue. So it can actually drill at an angle, so shouldn't be an issue. Drilling parameter can easily be changed during machining, notification of suppose. You can read the rest. I'm just looking at things that's not easy to understand. So the cost is relatively small compared to other processes used to produce very small holes. So if you're looking at producing a small hole in the range of microns, then this is one of the cheapest way of doing it. Okay? Limitations of EBM. The primary limitations are the capital cost, the high capital cost of equipment. So the initial investment is quite expensive because the EBM equipment itself is quite expensive. And necessary regular maintenance applicable for any equipment using vacuum system. So because of the vacuum system, it's expensive to maintain. So the initial capital cost is expensive to buy the equipment. And maintenance of the system is also quite expensive, especially for the vacuum system. Yeah. The process also need a very high energy consumption. So the running cost of the electricity will be high because energy consumption is very high. And you require highly skilled operators. So you cannot just use operator that does not have technical knowledge, because the adjustment, the maintenance, so on so forth, needs somebody that understand the operation and the physics behind the. So it requires high skilled operators to do this. Only economical for small productions. So you're not talking about mass productions. You're talking, if you want to talk about mass production, let's say for example, making let's say for example, cans for the soft drink. I mean, it's not economical for that because the initial investment cost is high. Long production time due to the time needed to generate vacuum. So basically, for this to happen, you need to create a vacuum inside the chamber up to 5 millitorr, 5 times 10 to the 10 to the power 10 times 10 to the power of minus 5 torr. So in order for you to achieve that particular vacuum, it takes maybe about maybe 1 or 2 hours to do that. Yeah? in UTEM, we have a system that run on a vacuum system, and usually to get 10 to the minus 5 uh, torr in terms of vacuum pressure, then you need about 2 hours for the system to achieve that. It requires protections against X-ray, the impact of high velocity electron produce X-ray. So there's X-ray generated because of the high velocity of electron impacting the workpiece. So you need to have this protection. In presence of thin recast layer, resolidified layer. So one of the limitations of EBM, for example, if you have this, so if you look at this is the workpiece materials. This is the auxiliary material. So the electrons will impinge on the surface. So once it's impinged on the surface, then basically you melt the material. So as material melt, right? Then you have this taper at the center. What happened is as the molten metals vaporize and ejected from this particular hole, some of it will re-solidify on this surface. So that is what it meant by re-solidified layer. So there's a presence of a thin recast layer, re-solidified layer for this particular process, and it's impossible to get rid of that. So these are one of the limitations of this EBM process. And the drill hole has a slight taper and crater on the top. So because of that, you have a taper, and at the bottom you have a taper, and basically you have recast layer on the top and taper on the top. So if you look at this is the auxiliary materials. The electron melted and vaporized these particular materials. These materials will induce a high pressure and push the vaporized and molten metals out from this particular drill hole. But some of it will be landed on the entrance, and you'll have a re-solidified recast layer here. Any questions? Okay, so conclusions on EBM. EBM machining is one of the non-conventional thermal. So this EBM is a non-conventional machining under thermal process category. So the principle is use high velocity electrons beam to induce melting and rapid vaporizations of materials. So you convert the high velocity electrons that travel at about half a speed of light and impinge it on the workpiece. So you convert the kinetic energy into heat energy and vaporize the material. The equipment which works to generate the beam is called electron beam gun. Almost all materials can be handled using EBM process, machining process, which is one of the benefits of this particular techniques. Methods is also fit for micro machining, so it can do micro machining. So you're talking about micro level holes with the job of drilling fine holes, cutting narrow slot, and cutting contour in the sheet. However, the high capital cost equipment and the mandatory requirement for the high skill operator of the system should be taken into consideration before installment. So you have to look at the high capital cost incurred for the initial investment of the equipment, and also the skill set of operator to operate and maintain the system, and also the other issues with regards to the X-ray protection system, so on and so forth, to be taken into considerations before you purchase and acquire this particular system for production. So any questions on EBM? No? If no questions, then proceed with plasma arc machining, or in short is PAM. Yes, anybody want to ask questions? No? Okay, so let's move on to PAM, plasma arc machining. So so when you have a gas, you increase the temperature of the gas up to 2000. Then the gas molecules become disassociated into separate atoms. So this is talking about principle of a plasma. Just last time when we talk about plasma channel in the area of uh, what process? Uh, EDM process. EDM process. We talk about generating a plasma channel, right? But that is in the fluid. But if you want to develop a plasma, you want to ionize the gas, right? So you need to heat it up. You need to heat it up about, so if you have, let's say, for example, in the environment where you have CO2, so in the environment of a CO2 or N2, then the atom exists in terms of molecules. So if you heat up the gas up to 2000 degrees Celsius, then these gas molecules will separate into atoms. So rather than N2, then you have NN, right? Nitrogen atom and nitrogen atom. It's no longer in molecule shape, right? And if you heat it up for this particular process, plasma arc machining, you heat up to 30,000 degrees Celsius, then these atoms become ions, right? So because at that high temperature, then basically you can have you can eject the electrons out from the atom's orbit. So basically become ions, and you have electrons, free electrons, and you have ions. So the gas at this stage is the plasma. So whenever you have ions and electrons in the system, then basically you say that plasma exists in a particular system. Machining by plasma was adopted in 1950s as alternative methods for oxygas flame cutting of stainless steel, aluminum, and other non-ferrous metals. So basically, this is alternative to oxygas flame cutting because there are some benefits that this particular process, which is plasma machining, has. So in a plasma machining, the continuous arc is generated between the hot tungsten cathodes and water-cooled copper anodes. So basically, in this particular pump, plasma machining, so you have this is the cathode itself. So this is made of tungsten, right? And the water-cooled copper anode. So so there are two methods of a pump. Over here, the anodes is on the workpiece, but the anodes also can be somewhere here, and this is what is referred to. So I'm just going to go through. Okay. So if you look at machining system on pump before we go to the previous slide, so there are two methods. One is transferred, the other one is non-transferred plasma arc system. So on the transferred plasma arc system, basically the cathodes and anodes. So you have a tungsten. So this is the cathodes, and the anodes is workpiece materials. Right? So you transfer the arc between the tungsten cathodes to the workpiece, which is anodes. Okay, so this is called transferred plasma arc machining system. So you can also have another system which generate the plasma indifferently. So you have a tungsten over here, which is the electrode, and the cathode. And the anode is not the workpiece, but the anode is this guy, and this is what it meant just now is water-cooled copper anode, right? So when this explain it, a water-cooled copper anodes, the anode is referring to this anode, which is non-transfer arc system. So in plasma machining, a continuous arc is generated between hot tungsten cathodes and also water-cooled copper anodes. So this is for the non-transferred plasma arc system. Gas is introduced around the cathodes and flow through the anodes. So gas introduced around the cathodes over here and through the anodes, right? Through the anodes. So you have a gas stream going down here. The temperature in the narrow orifice around the cathodes reach 28,000 Celsius, which is enough to produce high temperature plasma arc. So the temperature in narrow orifice around the cathode. So around the cathode itself, around here, around here, around here, and around here, right? Around here, around the cathode itself, temperature is about 28,000 Celsius, which is high enough to produce high temperature plasma arc. So basically, mentioned just now, in a gas system, at 2000 degrees Celsius, then it becomes atoms. You heat it up in this particular process up to 30,000, 28,000 degrees Celsius. Then basically that particular atoms become ions and also free electrons. So under these conditions, metal being machined in a very rapid melted and vaporized, the stream of ionized gas flush away the machining debris as a fine spray created a flow lines on the mechanical surface. So basically, the temperature here is that high. So the gas, the working gas around the cathodes will push the plasma down and melt the workpiece materials. Okay. So again, there are two methods of pump system. One is called transferred method. The other one is called non-transferred plasma arc system. In the transfer method, then basically the anodes, the cathodes is your tungsten electrodes, and the anodes is the workpiece itself. The workpiece itself, and you have the rest of the system is the same. But then based on this, then you have arcing between the tungsten electrodes and also the workpiece material. For this particular system, basically the electrode is tungsten, is negatively charged, so it's cathode. The anode is the copper, which surrounding that particular cathodes. And basically there's plasma gas generated because of high temperature. Then you push the plasma gas down to the workpiece materials. And in both cases, usually you have a shielding gas. You have a shielding gas around it. And the purpose of shielding gas will be discussed later on. So in the non-transfer method, the arc occurs between the electrode and the nozzle, and the heat is carried to the workpiece by plasma gas. This transfer, thermal transfer mechanism is similar to that of the oxy-fuel flame. So this is similar to oxy-fuel flame. Any questions so far on pump? Okay, technical considerations for pump. There are a few technical considerations that we go through one by one. Material type, the thickness, cutting speed, cut quality, so on and so forth. So material type, carbon steel, aluminum, stainless steel are the most commonly cut with plasma arc. So usually you cut carbon steel, aluminum, and stainless steel. Many other metals may be cut with plasma, including nickel alloys, brass, so on and so forth. Right? So basically, this particular process can cut wide range and variety of materials. In terms of material thickness and cutting speed, workpiece thickness is one of the considerations whether plasma cutting will be cost effective or not. The maximum cutting speed depends not only on the thickness but also in the power supply in the material. So we're going to look into this later on in a bit detail in terms of how the thickness dictate the cutting speed, so on and so forth. So this is the typical chart between the maximum speed and workpiece thickness. So this is looking at the N2 gas as a gas, as a working gas, and CO2 as a secondary gas. So secondary gas is the shielding, and N2 is the working gas that change into plasma. So based on this setting, Then basically, if you look at the graph, so this is for the carbon steel, this is for the stainless steel, and this is for the aluminum. So this is looking at the maximum speed that you can use based on the thickness, right? So as the workpiece thickness getting higher, then the maximum speed become very low. So this is what it meant by this particular statement. The workpiece thickness is one of the considerations whether plasma cutting speed will be cost effective or not for your operations. So based on this, for example, if you're talking about the material, if you're talking about aluminum, and you're talking about the thickness about the 35 mm, so you're at this rate, and your maximum speed is about 0.8 meter per minute. So based on that, then you have to make assessment whether this speed is good enough, economical enough for your application or not. So this is one of the consideration that you have to think about. Other technical considerations in PAM, cut quality. Cut quality is affected by the type of metal and cutting speed. Process variables such as cutting gas, power, speed are adjusted to provide optimum cutting speed for each metal. Although the size of the power supply is a factor, cut in metals up to 2-inch in thickness tend to be smooth, while cut in the thicker section may be rougher, but still clean. So you're talking about in terms of cut quality, you're limited to about maybe 2-inch of thickness. Then you can have quite a smooth cut. If it's thicker than that, basically you're going to have a rough cut, but it's still clean. So it depends on your applications. Cutting specifications, for application where high quality cuts is needed, some requirement must be considered as the first one is tolerance, amount of bevel, dross, heat affected zone. So tolerance is basically the tolerance that you can your parts can take. So plasma cut to a closer tolerance than flame process oxy-fuel. So comparing to oxy-fuel, this is much better in terms of tolerance. Because of faster cutting speed, heat of the workpiece, because of the cutting speed, heat the workpiece less, resulting in less distortions. So plasma is capable of tolerance 1/32 inches in materials under half an inch. So if you're talking about tolerance for materials under half an inch of thickness, then the tolerance is 1/32 inches. Right? But this tolerance depends on the type of material, thickness, and power supply. Plasma cutting produces a bevel cut, forming wider cut on the top. So things that you have to remember that it will produce a bevel cut, look like this. So wider on the top than the bottom. The bevel can be easily corrected or reduced by special techniques or equipment. So you can do reworking, so on and so forth. Generally, the amount of bevel is less for thinner materials. So the thinner the materials, then the smaller the bevel cut is. The other things that you need to watch out for is the dross. So for this particular techniques, you're going to have a dross. Dross is basically the material left over at the bottom of the cut. So if you look at this drawing, so there's a dross here, there's a dross here. So basically this is, once you cut it, there's molten metal. Then this some of the molten metal will actually place itself at the bottom of the cut, as shown here. So you're going to have some dross here. If that's not acceptable, then you have to make a secondary operations to remove it. The other thing is heat affected zone. So there'll be some heat affected zone to a certain thickness on the surface of the mission surface. So you have to take that into consideration. So in terms of cutting specifications, you have to be aware that there are some tolerance limitations. The cut is bevel, so there'll be some dross at the bottom. And due to the heat, then there's a heat affected zone on the cutting surface. Some of the considerations in PAM, cutting gas. The cutting gas selected depends on the speed and quality of the cut desired. So the cutting gas is this gas. This gas, the gas that going through here. So that's a cutting gas, right? So this is the gas that will be converted into plasma. So the cutting gas depends on the speed and force. Nitrogen is widely used because it's relatively inexpensive. So usually we use nitrogen because it's cheap and can be used for many materials and thickness. Special mixture of argon and hydrogens can improve the cutting speed and quality of thickness, thicker metals, those other than carbon steel. So sometimes people use argon and hydrogen because of that particular reason. Oxygen is used in combination with other gas to improve the cut quality by increasing the heat. So you can also use oxygen because if you use oxygen, then the plasma generated using oxygen is actually is contain more heat. So because of that, it can cut faster. So because of that, then you can improve the cutting speed. Yeah. Compressed shop air is popular in many applications also because it's inexpensive and provide good quality of cuts for thickness under 1 inch, especially on carbon steel. So if you just want to use carbon steel, cut carbon steel, thickness is under 1 inch, then you can use compressed air, which is cheaper in cost. In terms of power supply, depends on the material thickness and cutting speed. Increase the power, increase the cutting speed, or enable thicker materials to be cut without slowing down. So power rating are commonly between 20 to 200 kilowatts. So if you use higher power, then basically you can increase the cutting speed, but use more power and enable thicker materials to be cut without slowing down. Any questions? Okay, some other application of pump. Basically, pump is attractive turning methods for difficult to machine materials by conventional methods. So you can actually use you can use a pump as a turning method, just like turning operation. Right? So let's say for example, this is a workpiece. You want to reduce the diameter of this workpiece. So you put this particular, if you can put this particular workpiece on a spindle and rotate it, then you can put a pump over here, right, at an angle, and basically as this workpiece rotated, just like turning operations, then basically pump can actually remove these materials as it rotates. So basically this is rather than having, let's say for example, turning regular cutting tools in here, you can use pump to actually reduce the diameter of this particular workpiece using this particular methods. So this is a spindle rotating. So this is a pump, and you can move it down to reduce the, so the torch feed is in this way, right, as this is rotating. So you can reduce the diameter of a shaft from this diameter to this diameter. So this is turning method that can be used using pump plasma arc machining process. Other application of pump, CNC pump is used for profile cutting of metals that are difficult to tackle by oxy gas techniques such as stainless steel and aluminum. So a large number of cut can be produced one sheet rather than eliminating shear operation. So rather than using shear operation, you can use this. You can stack it up and then do multiple cutting process using this particular methods. Some other application can cut grooves in stainless steel 10 times at the rate of grinding and chipping methods. So in terms of the speed, material rate, this is much better, 10 times at the rate of grinding and chipping methods. So if you want to cut grooves like this, low machining rates are obtainable when the grooves are cut in non-conductive materials. So lower machining rate obtained when these grooves are cut in the non-conductive material. So if it's non-conductive, it's lower rate. A groove dimensions, however, depends on the transverse speed out power and angle and height of the plasma. So you can make this proof using PAM process. And PAM is also has been used and can be used for welding operations. So basically, this is PAM. This is place to be welded. So this is your uh, the filler materials for the weld. So you can do welding operation using PAM. Other application of PAM is cutting tubes, wall thickness up to 50 mm, and without any deburring. This is underwater plasma cutting can be achieved. So if you want to do plasma cutting underwater, you can also use this particular process. Advantages of PAM requires no complicated chemical analysis or maintenance. So basically, it's quite simple to run. No harmful quarantine fluorocarbon solvent or acid cleaning chemicals need to be used. Plate cleaning often eliminate the need for vapor degassing, solvent wiping, ultrasonic cleaning, grid blasting. So the cut is clean. So you don't need secondary operations to finish up the machining process. Requires no workers exposure to harmful chemicals. Need less energy to operate. So this particular process need less energy compared to the other methods relatively. Some disadvantages: large power supply needed. So you are talking about large power supply. Even though it says here need less energy to operate, but if you compare to conventional machining, is still higher compared to conventional machining. But it's less than EBM process, electron beam process. The process also produces a heat that could spoil the workpiece and produce toxic fumes. So since burning happened, there might be possibility of toxic fumes, depends on the material that you burn. So you have to be aware of that. Again, high initial cost of equipment because of this heat related material removal process. You have a large heat affected zone that you have to be aware of. Rough finishing, surface finishing requires secondary process if necessary. So the finishing is not as smooth as other processes. So depending on the depth and also the speed, uh, you might need a secondary process to do it. Difficult to produce the sharp corners. So basically, you're going to have a bevel cut. So it's very hard for you to produce sharp corners. Smoky and noisy environment because of the melting and vaporizations. And basically, burr occurs. It's not really burr, but it's a dross build up at the bottom. So that need to be removed if your particular product required that.